Phoenix A is awake. Imagine driving across the entire continental United States, coast to coast, New York to Los Angeles. That trip is roughly 2,800 miles. Now imagine doing that drive 300 times. That's the diameter of our sun. Okay, now multiply that by 420,000. That's the size of the black hole I'm about to tell you about. And here's the part that should make the hair on the back of your neck stand up. Scientists just confirmed that after what may have been hundreds of millions of years of complete silence, it woke up. It's feeding right now, and it's doing something that by every law of physics we currently understand, simply should not be possible. This is the story of Phoenix A, the most extreme object ever discovered in the known universe. And the closer we look at it, the more it breaks everything we thought we knew. Stay with me, because after this, you'll never call anything in space impossible again. Chapter 1, the black hole that broke the textbooks. For most of modern astronomy, black holes came in two neat flavors.
First, you had stellar mass black holes, the collapsed remnants of dead stars, ranging from about 5 to maybe 100 times the mass of our sun. Think of them as cosmic potholes. Dangerous if you stumble into one, but manageable on a universal scale. Then you had supermassive black holes, the giants that anchor the centers of galaxies. These range from a few 100,000 to a few billion solar masses. The one sitting at the center of our own Milky Way, a black hole called Sagittarius A star, clocks in at around 4 million times the mass of our sun. That sounds enormous, and by human standards, it absolutely is. But here's what the textbooks didn't account for: a third category that nobody expected. Starting in the early 2000s, astronomers began spotting something troubling. Black holes at the centers of certain galaxies that were simply too massive to explain. Not a little too big, not marginally outside the expected range. Off the charts. We're talking objects that dwarfed anything previously imagined. One galaxy, cataloged as NGC 1277, was found to contain a black hole originally estimated at up to 17 billion solar masses. That's not a rounding error, that's a monster in a galaxy that, from the outside, looks perfectly ordinary. Then there's the quasar, TON 618, more than 10 billion light years away, harboring a black hole estimated at around 66 billion solar masses. Astronomers eventually coined a new term for this category: ultramassive black holes, objects exceeding 10 billion solar masses, and possibly climbing far higher than that. And then came Phoenix. In 2010, the South Pole Telescope, an instrument originally designed to map faint radiation left over from the Big Bang, picked up a subtle distortion in the sky, a faint smear of heat and light pointing towards something extraordinary. What followed was an all-hands-on-deck investigation involving optical telescopes, X-ray space observatories, and radio dishes across multiple continents. What they found was a galaxy cluster, a gravitationally bound swarm of thousands of galaxies with a combined mass of roughly 2 quadrillion suns. Scientists named it the Phoenix Cluster, after the constellation in which it appears. And buried at its very center, inside a single massive galaxy, was a black hole that defied classification. Current estimates place its mass at somewhere around 100 billion times the mass of our sun. Let that settle for a moment. Our entire Milky Way, with its 200 billion stars, its gas clouds, its dark matter, its planets, has a central black hole of 4 million solar masses. Phoenix A is roughly 25,000 times larger than that. The textbooks needed a rewrite. Chapter 2, a scale your brain was never built to handle. Here's where it gets genuinely hard to process, and I want to try to make it real for you. The size of a black hole's event horizon, the point of no return, where not even light can escape, scales directly with mass. Double the mass, double the event horizon. Sagittarius A star,
the black hole at the center of our galaxy, has an event horizon roughly 15 million miles across. That sounds enormous, but our solar system would swallow it whole. Phoenix A is something else entirely. If the higher mass estimates are correct, its event horizon stretches approximately 180 billion miles from center to edge. End to end, that's a diameter of around 370 billion miles, roughly 100 times the distance between the Sun and Pluto. Think about that in terms of America's greatest engineering achievement, the interstate highway system. If you drove every single mile of US interstate highway, all 48,000 miles of it, about 7.7 million times back to back, you'd finally cross Phoenix A from one side to the other. Light, the fastest thing that exists, would need 3 full weeks to make that crossing. But here's the twist that most people never hear about. At this scale, crossing the event horizon wouldn't feel like anything at all. Near a smaller black hole, a stellar mass one, the gravitational forces on either side of your body are so dramatically different that you'd be stretched apart like taffy. Spaghettification, scientists call it. Not a gentle way to go. But Phoenix A is so vast that the difference in gravity from your head to your feet at the event horizon is almost negligible. You could drift across that invisible boundary, the point where the universe permanently loses track of you, without feeling a single thing. No alarm, no jolt, no warning label. You wouldn't know you were doomed. The reckoning would come later, somewhere deep inside, hours or days after you crossed a line you never saw. And there would be no way to tell anyone. No signal would reach the outside. Phoenix A doesn't feel like a predator. It feels like a territory, a region where the universe you know simply stops applying. Chapter 3. How does something this massive even exist? This is the question that keeps astrophysicists up at night. The standard model for how supermassive black holes form goes something like this. A black hole forms from a collapsing star. It slowly accumulates gas over millions of years. When galaxies merge, their central black holes eventually find each other and combine. Repeat this over billions of years, and you can build a black hole of 1 billion solar masses. The math works, barely, and under ideal conditions. For Phoenix A, the math doesn't work at all. The universe is approximately 13.8 billion years old. To grow a black hole of 100 billion solar masses through normal feeding processes, you'd need it to consume matter at near maximum theoretical efficiency, continuously, for virtually the entire history of the cosmos. No pauses, no slowdowns, no burps. Real black holes don't behave that way. When they feed, the radiation they produce pushes outward, throttling the inflow. They cycle, they choke, they rest. So scientists are left with 2 uncomfortable possibilities. Option 1. The seeds of ultramassive black holes weren't stars at all. In the chaotic first moments after the Big Bang, enormous clouds of primordial gas may have collapsed directly into black holes, skipping the stellar phase entirely. These direct collapse seeds could have entered the universe already weighing tens of thousands of solar masses, giving them a massive head start. Option 2, in the early universe, entire galaxy clusters, not just individual galaxies, collided and merged. These titanic events could have funneled multiple supermassive black holes into the same gravitational well at roughly the same time, where they merged into something orders of magnitude beyond anything that came before. Either way, the conclusion is the same. By the rules we understand, Phoenix A has no right to exist at the scale it does. And yet, there it is. Chapter 4. The Broken Thermostat. Why Phoenix A is feeding right now. Here's where the story gets strange in a different way. Galaxy clusters are filled with hot plasma, a thin, scorching gas heated to tens of millions of degrees, hot enough to glow in X-ray wavelengths. This plasma slowly loses energy and cools over billions of years. As it cools, it falls inward under gravity toward the cluster's center, where it should compress and ignite into new stars at staggering rates. In most clusters, that never actually happens. Here's why. As gas cools and falls inward, it feeds the central black hole, which launches powerful jets of energy outward. Those jets reheat the surrounding plasma. The cooling slows, the infall stops. It's a natural feedback loop, a cosmic thermostat, and it keeps most galaxy clusters in a stable equilibrium. In the Phoenix cluster, the thermostat is broken. The cooling gas is winning. The central galaxy at the heart of the Phoenix cluster is currently producing new stars at a rate of 700 to 1,000 solar masses per year. For comparison, the entire Milky Way, our home galaxy, 100,000 light years across, forms roughly one new solar mass star per year. Phoenix's central galaxy is building new stars at nearly 1,000 times the rate of ours. Stars are being born there the way cars roll off an assembly line. It is one of the most extreme star-forming environments ever identified in the observable universe. And feeding all of that is a runaway cooling flow, a torrent of plasma pouring inward toward Phoenix A faster than its jets can push back. Why? Two leading explanations. First, the Phoenix cluster is unusually compact for its size, concentrating mass in a smaller central region and creating a steeper gravitational well that funnels gas inward faster than average. Second, the cluster appears to have avoided the major mergers that typically stir up cluster gas and prevent runaway cooling. It's been left alone long enough for the gas to settle, cool, and fall. Whatever triggered it, what we're watching is this: a black hole the size of a small city in space-time. An object with the mass of 100 billion suns that cannot keep up with its own meal. Chapter 5. What Phoenix A means for everything we think we know. We found Phoenix A partly by accident, because its host cluster was unusually bright in X-ray surveys. The runaway cooling flow made it stand out. But the black hole itself? It's quiet by the standards of feeding black holes. It doesn't advertise. Which raises a deeply unsettling question. How many others are out there that we simply cannot see? Most ultramassive black holes would be dormant, their fuel depleted, their galaxies starved of fresh gas. Dark, silent, invisible to our current instruments precisely because they've stopped doing anything dramatic. We'd have no way to find them. Some theorists have begun using a term: stupendously large black holes, for objects potentially exceeding 100 billion solar masses, perhaps by a wide margin. We don't know how many exist. We don't know what role they play in shaping the fate of the structures around them. We don't yet have the tools to count them. What we do know is that the light we're using to study the Phoenix cluster right now began its journey 5.7 billion years ago, before the Earth existed, before our sun had finished forming. That light has been crossing the universe for longer than our entire planet has existed, finally arriving at the telescopes we only just built. And what it's showing us is something we thought was ancient history: a black hole actively assembling itself in real time, a star formation explosion that mirrors what we think the early universe looked like. A system where every rule of astrophysical equilibrium has been thrown out the window. Phoenix A isn't just a record breaker, it's a window into cosmic processes we assumed were finished. Conclusion. Here's what I want you to take away from this. Every time humanity has looked deeper into the universe, past our mountains, past our atmosphere, past our solar system, past our galaxy, we've discovered that what we thought was the edge was actually just the beginning. Every largest thing ever found has eventually been replaced by something larger. Every impossible object has turned out to be just undiscovered. Phoenix A is the latest in that line. A black hole so massive that the word object barely covers it. A region of space-time so large that our solar system fits inside its event horizon more than 100 times over. a feeding event so extreme that it's producing stars at a rate 1,000 times faster than the Milky Way, and has been doing so for tens of millions of years. And yet, for all its incomprehensible scale, Phoenix A has been patient. It was sitting in the dark long before Earth existed. It will still be there long after our sun burns out. Every civilization that has ever risen and fallen on this planet, every empire, every discovery, every moment of human history happened in the time that light took to travel from Phoenix A to our telescopes. The universe doesn't stop being extreme just because we stop looking. So keep looking. Thanks for watching, and I'll see you in the next one.